Good morning, boys and girls, and welcome back with another day of working with derivatives. Today we're going to continue on with our discussion with the limit-defined derivative as seen below here. If we look at this, as we talked about yesterday, this is really just an application of slope, right? The f of x minus f of a over x minus a is just our, need a pen here. It's just our y2 minus y1 over x2 minus x1, right? We kind of showed with our setup yesterday. So the derivative, the point behind this is the derivative is just slope. The derivative is a slope function. It shows the slope of a graph. Okay? Technically we say it is the slope of the tangent line, but it's just the slope of the function. Okay, so just to reiterate here one last time, derivative is just slope. The derivative is a slope function, and if we want to find the derivative graphically, we are going to just sketch a slope function of the graph we're trying to find the derivative of. Let me show you. I have an example. Okay, here we have the graph of sine of x, and little Mickey here is going to help us graph the slope of this function. You can kind of see the tangent line in blue here. That's the slope of the tangent line, or the slope of the graph, aka the derivative. And as we move Mickey, it is going to plot the slope of the tangent line. Okay, let's see if I can do this here. See, as I move Mickey, that's not going to work. I got to use this. As I move Mickey, there we go. As Mickey moves, you can see the slope changing. As we approach down here, the slope is approaching 0. See, and the red dots now, those are, as I approach 0 here, as we approach 0, that approach 0. So as I move Mickey, we can kind of see, and now I have a slope of -1. It's down at -1, coming up, slope of 0. And all this is doing for us is it's sketching the slope of the function. And as I do this, as we kind of do this, we can see that it's actually kind of, making a new graph. Go a little bit faster here. Trying to get this to all graph in. You can kind of see now. And maybe, through this example, we can see that if we graph the slope of sine, well, it looks like we get another wave. And what wave are we getting here then? Well, that looks like cosine. So the derivative of sine, the slope of sine, must be our cosine function. That's pretty cool. I like that. Okay, so using that idea that the derivative is just a slope function, if I give you the graph of any kind of function, we should be able to sketch the derivative. So we're going to start here just with a basic, a piecewise linear function. And we're going to try to sketch the derivative of this function. All right? Now, as we look at it, I'm just going to kind of do this bit by bit here. You could actually go find these points, the point here and the point here, and you could go and find, y2 minus y1 over x2 minus x1 and find the slope between those points, or we can just kind of count and look at what our slope might be. In this case, it looks like our slope going from here to here, I'm going down 1 over 1, so it looks like I have a slope of -1. So starting here, going to -2, I have a slope of -1. Okay. Then going from -2 to 0, that looks like we have a slope of 1. I rise 1, run 1, rise 1, run 1. So I was looking at on the last one. So now my slope here would be a +1 from here to here. Now on this, notice that I'm using open circles on this. Okay. At the endpoints and at the pointy parts of the graph, those have to be open because, again, going back to our limit definition of derivative, because of the limit, from the left and from the right have to agree. Now in this case, from the left here I have a slope of -1, and from the right I have a slope of 1. So at that point, the left and right don't agree, and therefore it's undefined. So what we kind of say, a general rule is, the pointy parts of graph are not differentiable. Okay, you cannot take the derivative of the pointy part of the graph because of that limit definition, because the left and the right don't match up. Those slopes are different. Okay. Then on this last we've got another pointy part, so open part right here. Now on this last one again, I have a negative slope again, and I'm going down 1 over 2. It looks like down 1 over 2, so -1/2. And so that's how I do the slope of this function. Or that's what the derivative of this function would be. Because those slopes are all constant, there'd be a bunch of little constant functions that kind of like that. Okay, here's another little bit trickier graph. we're going to try to sketch the derivative of. If we look at this one, the slopes of this, again, we're looking at the slopes to sketch the derivative. I've got positive slopes coming up here, and then it changes to negative slopes. So we can kind of see that at like a maximum value here, if I'm switching from positive to negative, I'm going to have a slope of 0 there. Same thing, I've got a negative slope switching to a positive slope, negative to positive. So again, at that minimum value, I've got to have a slope of 0. So when you're trying to sketch the derivative of a function, this is a very good place to start. Anytime you have a max or a min, okay, you're going to start by saying, hey, at those values, the slope is going to be 0. All right? And we're just going to sketch this here a little bit, but whenever I start looking at derivatives, trying to match derivatives, okay, start with mins and maxes, and those should have slopes of 0. So that's where we begin. Once I'm going from there, now the rest is just going to be kind of all, guessing and checking-ish. This, again, has a large positive slope. Okay? So maybe my derivative is going to start then like over here, a large positive number, and it's going to come down, and as I get closer to here, my slope, is a large number, but then it comes down, and then it kind of gets smaller, smaller, smaller till it gets to 0. So starting up high, smaller, 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 till it gets to 0. And then here it's negative, small negative, getting bigger negative, but then getting smaller negative again. Like maybe we're going from, like negative 1/2 to negative 1 back, negative 1/2. It's negative, and it's not getting super big. I mean, we can we're just roughly estimating. But, so small negative value to maybe like negative 1, but then it starts coming back again. So it'll kind of maybe look something like that. And then again, at the minimum value, we got to be back to 0. Because now I'm switching from negative to a positive slope. And the same with this positive slope. I'm at a small positive number, maybe getting up to, again, 1. Again, we're just roughly estimating this, just to get a rough idea what the graph would look like. And then, again, getting smaller back to 0. So maybe this one's going to look something kind of like, like that. And then now, as we go down this side, the slope is going to get bigger, negative again. Right? And I got negative, and there's going to be, negative 2, 3, 4, 5, negative 7. So this is going to, again, come down kind of like on the other side. Those numbers are going to get bigger. So maybe the derivative of this graph would look like that. All right. Now, if we know anything, I know we haven't talked about the power rule yet, but I know some of you guys are in physics. If you know anything about the power rule, this looks like an x to the 4th function, and that looks like an x cubed function. And so that kind of makes sense if you try to tie it in with what you know about the power rule. If you don't know about the power rule, don't worry. We're going to get to that tomorrow. All right? For now, though, either way, we just want to really focus on trying to sketch the derivative through looking at the slopes of the function. That's what we're trying to work on. Okay, here we go. Our last example of trying to sketch the derivative of a function just by looking at its slope. You can see, again, getting a little more complicated with our function. Going back now, we said we want to start, again, anywhere where we thought we had a 0 slope. So, again, kind of, using my tangent lines and kind of looking at these. Hey, this piece is all going to have, negative slopes. In general, we're looking for mins and maxes, negative slope going to a positive slope. So, right about here, right at this min, our derivative is going to have a 0 slope. So I want to go put a dot right there. Everything else, these are all going to be now like, negative slopes again. So that's not going to work out. All right. Now, I'm going to go and look at this. Again, at these places where the asymptotes are at. Okay, the derivative is going to be undefined since there is no graph there. Our next part, I'll talk about that a little bit more. And then another place, I just kind of look. I know these all got to be negative slopes, we said, right? If I look at the tangent lines to this piece of the graph. But I just kind of go and be like, okay, well, if I'm trying to be specific with my slopes, I then try to look where do I think it might have a slope of, like negative 1. So maybe, right in here somewhere. This would have a slope of negative 1. Again, I know I don't need it on the y-axis, but I'll just put a dot right there. And then as I go this way, my slopes are going to be getting smaller. So since they're getting smaller, I've got to approach the x-axis. So it might look kind of like that. As I go this way, my slopes are still going to be negative. Again, they're becoming steeper, right? A larger negative number. So as I go this way, my slopes are going to become larger in the negative direction, or go down like that. So in this case here, this piece of graph, the derivative, looks an awful lot like the function itself, right? Fairly similar. All right. Now this one here, I start and I've got, again, a large negative slope, it looks like, right? Then getting smaller, -1. You know, if you want to, hey, -1, maybe like right here, that has a slope again of -1, you know, to 0. And then now, you know, it's a positive slope, and maybe like right in here somewhere, we're at like +1, you know, and then getting bigger as I approach there. So negative number, large negative number, kind of comes through here to a large positive number. So the derivative of that piece would look kind of like that, potentially. That makes sense. And then now in this one here, again, we said these are all, again, going to be negative slopes if I'm thinking about the tangent line to this function. Okay, and again, like maybe right in here we have a slope of -1 again. And then, you know, as I'm going this direction, the slopes are becoming becoming smaller, right, closer to 0. So as I go this direction, it's got to go smaller, closer to 0. And as I go this direction, they'll become bigger in the negative direction. So the derivative of this function would kind of look like that. Okay? So we kind of want to look at these tangent slopes, the slopes of the function, to help us sketch the derivative. Because again, the derivative is just a slope function. The derivative is the slope of the graph. All right, last thing we need to do here is we need to just have a little conversation about continuity and differentiability. Okay. First of all, differentiability means that you can take the derivative of a function, that the function has a derivative. All right. And what we know then is that differentiability implies continuity. Okay. If a function is differentiable, if it has a derivative, then it has to be continuous. Okay. Differentiability implies continuity. If it's not continuous, then you can't have a tangent line slope at that point, and therefore it's not differentiable. So if we go back to our geometry days, that statement I just said there is called the contrapositive. Right? We go back to our if-then statements. If a function is differentiable, then it is continuous. Okay? The contrapositive is when you switch those and negated them. If a function is not continuous, then it is not differentiable. Okay? If it's not continuous, that implies that it's going to be not differentiable. Both of these statements are true. However, we got to be careful because the converse and inverse of the original statement. If a function is differentiable, then it is continuous. The converse of that statement is if a function is continuous, then it is differentiable. Okay, and that's not true. That's the converse. Again, the converse, remember we just switched the order. Okay, if a function is continuous, then it's differentiable. Not true. Just because a function is continuous doesn't mean it's differentiable. Going back to the very first one we talked about, right, when we had, you know, and again, I could relate this back to the absolute value of x. Y equals absolute value of x. This is a function that is continuous, but it's got that pointy part of the graph, right? And so because those slopes don't agree coming from the left and the right, then it is not differential at that point. So just because a function is continuous does not mean it has to be differentiable. And the inverse also is not true. Okay? The inverse is if a function is not differentiable, then it is not continuous. You just negate the two things. If a function is not differentiable, then it's not continuous. Well, again, this function is not differentiable, but it is continuous. Okay? So these two things we got to watch out for, stay away from. Don't get them confused. Those are not true statements. The true statements that we really need to focus on that is if a function is differentiable, then it is continuous. And it's contrapositive. If a function is not continuous, then it is not differentiable. Okay? Those two things are true. True. All right, boys and girls, that is it for today. Go get after it, and let me know if you have any questions. Have a good one.